Let's take a look at the Beta-Bernoulli model. Beta-Bernoulli. So this is a model where we have, for example, a sequence of binary outcomes like coin flips, and we model those as Bernoulli random variables with a beta prior distribution on the probability of heads. So beta is a conjugate prior for Bernoulli, so this will be an interesting case to analyze for Bayesian analysis. So we've got the setup is we've got some x1, x2 up to xn, which are Bernoulli, Bern for Bernoulli, and they have some parameter theta. So this is the probability of heads. And we'll put a beta prior distribution, so on theta, and so theta will be beta, let's say with parameters a and b. So here, the probability probability of x1, I'll say it this way. Probability that, so if x is Bernoulli with parameter theta, then just some generic one of these, then the probability that x equals 1 given theta equals just theta, right? The probability of heads. And theta has a density. Probability of theta is, well, I'll write it this way. We'll just write it out. So it's equal to theta to the a minus 1 times 1 minus theta to the b minus 1 divided by the beta function of a and b. So this is proportional to theta to the a minus 1, 1 minus theta to the b minus 1. Oftentimes it's just easier to work with the proportional thing. So that's the setup for our model. And now let's compute the posterior distribution. So first let's observe that the beta is conjugate to Bernoulli. So let's compute the posterior distribution on theta given some data. So we'll call this let's say we've got some data here, dx1 to xn, and we're using this setup to model. The posterior distribution, well, it's going to be proportional to, as a function of theta, proportional to probability of the data given theta times the probability of theta, just using Bayes' rule. And this becomes, this becomes probability of theta times this product, right? And this is, well, I could write it this way, p of xi given theta. So let's plug these in and we'll see what happens. So I'm using this as a shorthand for, sort of p of x. Well, I guess, or rather p of 1 here. I guess given theta. So if we plug these in, this is proportional to, we'll make it proportional to since we're already using proportional to here. It's proportional to this guy, theta to the a minus 1, 1 minus theta to the b minus 1, times the probability of all these. And each of these can be written as, right, this could have been written as here. This was equal to theta to the indicator that x equals 1 times 1 minus theta to the indicator that x equals 0. And so we can write this as theta to the sum of the indicators that xi equals 1. I guess that should be little xi. Or no, I guess it's, well, this is my shorthand for probability that capital Xi equals little xi. So this would be, I guess, what would it be? So this would be, yeah, we'll just put it this way. Little xi equals 1. 1 minus theta to the sum of the indicators that little xi is equal to 0. So let's give these two things some names. Let's call them N1 and N2. So that if we call this N1, the number, so what is this? This is just the number of xi's that are equal to 1. So we'll call that N1. And I guess it would be better maybe rather than 2, let's call this N0. This is the number of xi's that are equal to 0. So this is just the same. Theta to the N1, 1 minus theta to the N0. And we can pull these together, and we get A plus N1 minus 1, 1 minus theta to the B plus N0 minus 1. And we were trying to show that this posterior distribution, well, our first step was we wanted to show that the beta is conjugate to the Bernoulli. So we wanted to show that this posterior distribution on theta is a beta distribution. Right? That's the definition of a conjugate prior. It's a family such that the posterior is also a member of that family. And we've got that, right? Because here, this is, we can write this, beta, using this shorthand. It's the density of a beta function, of density, well, it's proportional to, I should say, not equal to. It's proportional to the density of a beta distribution with parameters a plus n1 and b plus n0, right? See, we're just matching these two expressions up here. So that implies we have our first result, that the beta is conjugate to, so this posterior distribution is this beta with, well, I just writing the same thing here, b plus n0, separate from that. And so this shows that beta is conjugate to Bernoulli. All right. So that's good. That's nice. Now, a beta distribution, let me just draw a little example, a couple little examples here. A beta distribution, if you recall, I guess I should have, to be more precise here, I should have included an indicator function, because it's only, the support of a beta distribution is only between, so I should have included an indicator function here that theta is in the interval between 0 and 1, to be more precise. You know, this should be multiplied by that indicator. So a beta distribution is its support, the part where it's non-zero, the closure of the part where it's non-zero, is on the interval from 0 to 1. And some examples, so well, a uniform would be a special case. If we took a and b equal to 1, then this would just be a constant. So uniform is a special case of that. So this would have to go here also. So then you can also get some crazy things like, you know, well, it could go up like this. It could spike at the endpoints. It can do all kinds of interesting things by varying the a and b. So that's a beta distribution. And let me mention, so it will be useful to know for our posterior like the posterior mean and the posterior mode and so on and so forth. So let me say, in general, for a beta distribution, we'll put it this way: if x is beta with a parameters a and b, then the mean of x is just a over a plus b, and its variance is, well, I'll go ahead and tell you the variance. I don't know if we're going to need it here. I'm looking at a reference here for these. I don't remember them offhand. This is a plus b squared times a plus b plus 1. And the posterior mode, so I'll just put the mode, that's where the density is maximized, is a minus 1 divided by a plus b minus 2. So using this is true for just a general beta distribution. And now let's apply these little just facts. I didn't prove them, but they're not too hard to prove. Let's apply these to our posterior distribution. So that's if x is beta. And now, so theta, since theta, given the data, the distribution of this, the posterior distribution on theta given the data is this thing, this beta a plus n1, b plus n0. That implies that the posterior mean, the expected, not x, the expected value of theta given the data, the posterior mean is this thing, but now we use these parameters, so it's a plus n1 divided by a plus b plus, let's say n1 plus n0 is, well, it is actually, so it is n. We already defined n, and in fact that's right, because it's n1 was this, the number of ones, n0 was the number of zeros, and we had n points total, so the sum of those is just n. So that's the posterior mean, the mean of the posterior distribution on theta. And the variance, well, we could write down the variance and so on and so forth. I'll write down the mode just to, because that'll be useful in a second. The mode of this guy is a plus n1 minus 1 divided by a plus b plus n minus 2. Right? I'm just plugging these numbers in here. All right. So that's nice. Now we computed the posterior. That's what we did above. And now we can just immediately get these nice summary statistics of our posterior. So let me tell you just a little bit of terminology here. These parameters, a and b, in general we call these hyperparameters. Not just in this case, but more generally, whenever you put a prior on your parameters, then the parameters of the prior are called the hyperparameters. Hyperparameters. It's one word. Okay. And in this case, in this particular case, since these n1 and n0 are in some sense the counts for this distribution, that it was the number of times, these are often referred to as the counts, then the a and b, since the posterior takes this form, these are often interpreted as sort of pseudo counts. So people will often call these a and b, they're called pseudo counts of the prior distribution in this special case, since they have this sort of interpretation. Okay, so this was some basics, and I'll make a couple more observations about this in another video.